In this video, I'm going to go through the problem-solving steps and go through a series of problems from Chapter 2, which should cover all the various different types of problems that you should encounter. So first of all, when you solve a problem, no matter how complicated it seems, if you follow this recipe, you should be able to do any problem, or at least go far enough to get a majority of the points on it on the test. Okay, so first of all, read the whole problem and make sure you understand what it's talking about. Read it twice. Decide on what object is it that you're studying, what is it that's moving, and what's the time interval that you're interested in for the problem. The most important thing is draw a picture. It just can be a simple sketch, and choose what coordinate axes. So is the thing moving horizontally or is it moving vertically? Do you want to use X or Y? Then write down all the things that you're given in the problem and the things that you still need to find. And then, using your answers from 4, which equation do you need to pick in order to relate the unknown and known variables to each other? And then once you've done that, you can solve the equation that you picked algebraically for the unknowns and check that your result is sensible. Okay, so calculate your solution after you've done the algebra and round it off to the appropriate number of significant figures. And then finally, look at your result. Is it a reasonable number? Make sure you don't have someone who's jogging at 500 miles per hour. That would just be ridiculous. Okay, and finally, check all your units. So write down your units for each thing. Make sure that they're sensible units and that they agree. So if you have a speed, it should be in meters per second or miles per hour, for example. Okay, so let's get going, and we'll start with a simple problem. Okay, so the first problem says, when striking, a predatory fish can accelerate from rest to a speed of 4.0 meters per second in 0.11 seconds. What is the acceleration of the fish during the strike? And B, how far does it move during the strike? Okay, so what are our rules? Well, the first rule was read the problem and then read it again. So we've read it once, let's read it again. We have a fish that's when striking, it can accelerate from rest to a speed of 4 meters per second in 0.11 seconds. In part A, they're asking us what's the acceleration, and in part B, they're asking us how far does the fish move during the strike. Okay, so what is it that we're studying? Well, what we're studying is the fish, and what's the time interval? We're studying it over the time from which it accelerates from rest to 4 meters per second. Draw a diagram. Okay, so draw a simple sketch. So here, I'm going to draw a sketch here. I've got my fish. It starts off at rest. So V equals 0. It goes along a certain distance, and it ends up at a V of 4.0 meters per second. And I know that my time difference is 0.11 seconds. So what I always do when I draw a picture is I already start to pull out the things that I know and that I don't know from the problem. Okay, so I've got my time. Do I know my distance? No, I don't know the distance. That's what I have to find in part B. Okay, so let's write down what we know and what we don't know. And so we have 6 things always in these problems in one dimension that we need to find. We've got final and initial position, final and initial velocities, the time, and the acceleration. So usually, unless you're told differently, we always take the initial position as 0. Okay, so we start off at 0. Our final position, we don't know. That's what we're asked to find in part B. How far does it move? Initial velocity, well, reading the problem, it says the fish starts from rest. So it starts from rest, and that's 0. The final velocity, he's going to a speed of 4.0. And our units for the speed are meters per second. And we're going to do everything in SI units, so we'll make our position be in meters. So I'll write down meters there. All right, time, do I know how much time it takes? Yes, it tells me it takes 0.11 seconds. So I'm going to write down 0.11 seconds. And what is the acceleration of the fish? We don't know that. That's what we have to find in part A. Okay, so we know 4 things and we need to find 2 things. So next thing to do is to figure out what equations it is that we're going to use to relate the known and unknowns. Okay, so what's our coordinate system? Well, the fish is moving horizontally through the water. It's not jumping up through the air. So we're going to use this top box of equations. We're going to use the ones for motion in the x direction. If we had something moving vertically, then we would use the equations in the y direction. Okay, so we're going to use the top set of equations. So we've got equation 1, 2, and 3, and I need to find x, and I need to find a. So I need to find an equation that's going to allow me to find the acceleration for part A using the things that I already know. So let's go through these equations. So first equation, equation 1. Remember, you can only solve an equation if you have only one unknown in it. So what do we know in equation 1? Well, in equation 1, we know v. We know v initial. We don't know the acceleration. And we do know the time. So that's an equation that we could use to solve it. And that's a pretty simple equation. So why don't we just go ahead and use equation 1 to solve part A. So for part A, I'm going to use equation 1. Okay, so I've got V is equal to V0 plus AT. I know everything except the acceleration. I need to rearrange this to solve for the acceleration. So I've got to do my algebra and get everything except for A on one side. So first of all, let's subtract V0 from both sides. So I've got V minus V0 is equal to A times T. And then to get A, I'm just going to divide both sides by T. So I get V minus V0 over T is equal to my acceleration. Okay, and now I know everything that's on the right-hand side of the equation, so I just put in the numbers. So V is my final velocity, 4.0 meters per second, minus my initial velocity, 0 meters per second, divided by my time, 0.11 seconds. So I get 4.0 meters per second over 0.11 seconds. And my answer for that is 36.36 meters per second squared. Okay. So my units that I ended up with is meters per second divided by second, meters per second squared, and that's the correct units for acceleration in the SI system. So I've checked that my units are correct. Next thing is round it off to the correct number of significant figures. So in this problem, how many significant figures am I given? I'm only given two numbers. I'm given 4.0 for the speed, and that's two significant figures. And I'm given 0.11 for the time. That's also two significant figures. So I need to round my final answer for the acceleration off to two significant figures. So I'm going to round that to 36 meters per second squared. And a good idea when you're doing a problem, especially on a test, is draw a box or a circle around your final answer so the person grading it knows what your final number is. Okay, so we've got the acceleration. In fact, I can go back up here and write it down. And I'm going to write it down with more significant figures than rounding, because remember, I might need to use that acceleration to calculate the distance for part B, and then I want to keep as many significant figures as I can and only round it off at the end. Okay, so now let's do part B. So now I know everything here except for the position. So I want an equation that's going to give me the position. So which equation am I going to use? Well, I can't use equation 1. Equation 1 doesn't have the position in it anywhere, so that's not going to solve anything for me. How about equation 2? Equation 2, I don't know the position. I know my initial position, initial velocity, I know time, and now I know the acceleration. So I could use equation 2 to solve for the position. I could also use equation 3 to solve for the position because I know initial and final velocities, and now I know my acceleration, I know my initial position. So you could use either one of those equations. I'm going to use equation 2 because it gives me x directly. I don't have to do any algebra, just directly substitute. Okay, so using equation 2, I'll get x is equal to x0 plus v0t plus 1/2 at squared. And now just plug in my numbers. So initial position, 0 meters. V0 is 0 times the time, which is 0.11 seconds, okay, plus 1/2 A. On my A, I'm going to put it in with my 4 significant figures, times the time squared. Okay. And if I plug that into my calculator, this middle one, of course, goes to 0 because I've got 0 times time. So I'm just going to get 1/2 times 36.36 meters per second squared times 0.11 seconds, all squared, and I get a position of 0.22 exactly meters. Okay, so I needed 2 significant figures, and I've got 2 significant figures. So there's my final answer for the position. Does that make sense? 0.22 meters, how far is that? 0.22 meters is about 22 centimeters. It's a little bit less than a foot. So that's sort of a sensible kind of distance that you can imagine a fish moving when it goes to catch a bug, for example. Okay. And the units, how do the units work out? Well, I've got meters per second squared times seconds squared. So the seconds squared cancel out and leave me with meters. So my meters worked out properly in the equation. Okay, so now I've solved this problem. I've solved 2 different equations, one to find the acceleration and one to find the position. Okay, so let's do another problem. Now this time we have a jet plane that's cruising at 250 meters per second when suddenly the pilot turns the engines up to full throttle. After traveling an additional 2.0 kilometers, the jet is moving with a speed of 300 meters per second. What's the jet's acceleration? So this problem is not much different in difficulty to the first problem we did. Just this time we have a jet plane instead of a fish. Okay, so read it again. We've got a jet plane cruising at 250 meters per second. Pilot turns the engines up to full throttle, goes for 2 more kilometers, and then it's moving at 300 meters per second. We want to know what's the jet's acceleration. Okay, so next thing we do is draw a picture and then try to figure out what we know and what we don't know from the problem. Okay, so we've got an airplane. Starts off at 250 meters per second. It travels 2 kilometers, after which it's going 300 meters per second. Okay, so what do we know and what do we not know? Initial position, we usually put that at 0. Final position is 2.0 kilometers. Initial speed is 250 meters per second. Final speed is 300 meters per second. How long did it take? What's the time frame for this problem? We don't know. And what is the acceleration? We don't know. That's what we're meant to find out in this problem. Okay, so what equation can we use? Okay, so remember what is it we need to find? We need to find the acceleration. So we want an equation that's got the acceleration in it, and we're moving horizontally, so again we're going to choose the equations that are moving in the x direction. Now every one of these equations has acceleration in it, so we need to eliminate them a little bit further. Okay, so first equation, what do I know? I know my v, I know my v0, I don't know my a, and I don't know my t. So I've got 2 unknowns in that first equation, so I'm not going to be able to use that equation. Alright, what about the second equation? Do I know my final position? Yes, 2 kilometers. Do I know my initial position? Yes, 0. Initial speed, time? No, I don't know my time. I don't know my acceleration. I don't know my time, so I can't use equation 2. Alright, so process of elimination, we must be able to use equation 3. Let's check it out. I know my v final, I know my v initial, I don't know my acceleration, but I know my positions. So I should be able to use equation 3 this time to solve the problem. Okay, so I've got my equation, and now I need to rearrange it algebraically to solve for the thing that we're asked for. So we're asked for the acceleration, so I need to get everything except the acceleration over on one side. So what I'm going to do is I'm going to subtract, first of all, get the v0 squared, subtract that from both sides. Okay. Now I can divide out everything except the a on this side to give me the a by itself. So I'm going to take v squared minus v0 squared, divide that by 2 to get rid of this 2, divide it by x minus x0, and I'm just left with just a. Alright, so my acceleration is the final speed squared minus the initial speed squared over twice the distance that it moves. Okay, so put in my numbers now. I've got final speed 300 meters per second. I'm going to square that. Minus my initial speed 250 meters per second, all squared. Divided by 2 and divided by the distance that it travels. Now, how far does it travel? It travels 2.0 kilometers. Now, remember, we're supposed to be using the MKS system, the SI system, where our distance is in meters. So we need to put x minus x0 in meters, not in kilometers. So 2.0 kilometers. There's 1,000 meters in 1 kilometer. Remember, if I convert my units, I need to write it in terms of a fraction where I cancel out now the kilometers. So kilometers goes on the bottom and meters on top. So 1,000 meters in 1 kilometer. So my distance in meters is 2,000 meters. Okay, so put that all together and I can solve for my acceleration. Okay, so plug that into my calculator. I get 6.875 meters per second squared. Okay, is that a reasonable number? Yeah, it's probably a reasonable number. It's not something like 10,000 meters per second squared. It's not something like 0.001. It's sort of a reasonable kind of looking number. Okay, how about significant figures? Well, how many significant figures do we have? If I look at all the things I'm given, initial speed, that's got 2 significant figures. The distance traveled is 2 significant figures. And the final speed, well, this could be 1, 2, or 3 significant figures. And so what I'm going to do for this one is I'm going to say that I've got 2 significant figures, since the other 2 things I'm given also have 2 significant figures. So I'm going to round this off to 2 significant figures. So 6.875 goes to 6.9 meters per second squared. Okay, are my units correct? If my units aren't correct, then that tells me I probably did my manipulation of the problem a little bit wonky. Okay, so let's check what I have. I've got meters per second, all squared on top. So that gives me meters squared per second squared as my units on the numerator. In the denominator, I'm dividing through by meters. So that gets rid of one of these meters, and that gives me units of meters per second squared. And that's the units that we expect to have for acceleration, right? Distance per time per time. So now we've got the answer to that problem completely done. Okay, so now let's do a third problem. Now I have a car that's entering the interstate, starts at 25 miles per hour, and you know that when you go on the interstate you have to be traveling a minimum of 50 miles per hour when you get on. The length of the access lane is 1,000 feet. So we want to know what's the car's acceleration as it accelerates to get onto the interstate, and how long will it take to travel the 1,000 feet. So when I say long this time, the long means time, not distance. Okay. So again, let's draw a picture. So I've got a car. It starts off at 25 miles per hour. It goes along the access lane, and it must be going 50 miles per hour when it gets on. And we know it travels a distance of 1,000 feet before it gets on. We don't know the acceleration, we don't know the time. All right, so let's put down what we know and what we don't know. Initial position, they don't tell us otherwise, so we're going to say 0. Our final position is 1,000 feet. Our initial velocity, the car starts off at 25 miles per hour. Final velocity is 50 miles per hour. Okay, how long does it take? We don't know. What's the acceleration? We don't know. Both of those things we have to find. Okay, so how do we solve this problem? Well, we just, again, do exactly the same thing. Look for what equations we're going to use. Again, we're moving horizontally, so we're going to use the top set of equations. All right, and first part, we want to find the acceleration. So let's look for what equation has acceleration. Well, all three of them. Which ones can we solve? Well, this is very similar to the last problem, right? So if I look at it, I don't know acceleration, I don't know time. So that means I can't use either equation 1 or equation 2 to get the acceleration. So I must use equation 3. So again, I've got v squared is equal to v0 squared plus 2a times x minus x0. And I can rearrange that in exactly the same way that I did the previous one to get my acceleration as v squared minus v0 squared over 2 times x minus x0. Okay, so now I put in my numbers. All right, so now if I look at my numbers, I've got miles per hour for the speeds, and I've got feet for the distance. Now you know we can't use mixed units. We could use units of miles and hours to solve the problem, or we could convert everything to SI and solve it in meters and seconds. Why don't we do it in both ways? So let's do it in both systems of units. So if I do it in, first of all, miles and hours, I need to convert my distance from 1,000 feet into miles. So 1,000 feet, I know that there's 5,280 feet in 1 mile. Okay, you can look up these conversions on the internet, or on a test you would be given the ones that you would need. I want to convert that into miles, so I want to cancel out the feet, turn it into miles, so I write it that way up. Okay, and if I do that, I get just under 1/5 of a mile. 0.1894 miles is my x. Okay, so now put in my numbers. I've got 50 miles per hour squared minus 25 miles per hour all squared over 2 times x minus x initial, and x initial is 0. X is 0.1894. Okay, so now plug that into my calculator, and I get 4,949.8 miles per hour squared if you look at the units. Is that sensible? Well, it's sort of hard for me to get a grasp on. It looks like a really big number, but those are really strange units. Okay, how about if we did that in meters per second? Because if we could do it in meters and seconds, then I have some sort of concept of whether it's a reasonable number or not. Okay, so how do we do that? Well, we've got to put our speeds into meters per second instead of miles per hour, and our distance into meters. Okay, so let's start with v initial, 25 miles per hour. We're going to have to convert the miles to meters, and we're going to have to convert the hours to seconds. So let's start with miles to meters. So I want to get rid of the miles and turn it into meters, so I write it that way up. We know there's 1,609 meters is 1 mile. Okay, now I need to get rid of my hours. So to do that, I'm going to have to multiply my hours. I want to turn it into per second, so seconds goes on the bottom. How many seconds in 1 hour? Well, 60 times 60, or 3,600 seconds. So I get 11.17 meters per second. How about V final? Do the same thing, except I'm going to start off with 50 miles per hour. I'm going to use exactly the same conversions. And as you'd expect, it's going twice as fast, so the number should be twice as big, 22.35 meters per second. Okay, and the position, I need to go from feet to meters. Okay. And I know the conversion between miles and meters. I know the conversion between feet and miles. So I'm going to do it like this. So I'm going to do the same thing that I did up here, where I got it in 0.1894 miles. And then I'm going to do this to go from miles to meters. So if I look at my units, my feet cancel out, my miles cancel out, and I'm left with meters. And that distance is 304.73 meters. Okay, so now if I put my numbers in, I get my acceleration is 22.35 meters per second, all squared, minus 11.17 meters per second, all squared, over 2 times 304.73. And remember, you don't round off at this stage. Only round off at your final answer. If you round off too early in a problem, you're going to get a number that's quite different from the correct answer. Okay, so plug in all those numbers, and what do I get? I get 0.615 meters per second squared, and to me that seems like a reasonable number. And you could equivalently have just done a direct conversion from miles per hour squared to meters per second squared with your final answer if you wanted to. Okay, so that's my answers to part A. Either one of those is correct unless you're told specifically what units you have to answer it in. You could do it either way. All right, part B, how long will it take? So part B, now I need to know what's my time. Okay, so I've got my acceleration. Let's put that in both units. Okay, so I've got my acceleration. The only thing I don't know is time. So which equation can I use? Well, I could use either equation 1 or equation 2 to solve for time. And I'm going to use equation 1 just because it's the simplest one. The least amount of algebra that you have to do, the more likely you are to get the right answer. Okay, so I'm going to use equation 1. V is equal to V0 plus AT. Rearrange it to solve for t. All right, so bring V0 over onto that side. So I get V minus V0 is AT. So t is equal to V minus V0 over A. In the first problem, we did exactly the same equation, but we rearranged it that time to solve for A instead of t. And that's what you're going to find when you do problems, is that you're always solving these same 3 equations. You'll just, depending on the problem, be solving for a different variable in the equation. So once you figure out how to do it one time, you should be able to do it for any problem. Okay, so now we just have to chug in our numbers. And again, we can do it in either system of units. So let's do it first in the standard system of units. So now I've got 50 miles per hour minus 25 miles per hour divided by 4,949.8 miles per hour squared. And that gives me a really small number, 5.05 times 10 to the minus 3 hours. And again, that's sort of hard for us to grasp. So let's do it in the normal SI system. Now our speeds, final speed 22.35 meters per second, minus initial speed 11.17 meters per second, divide by 0.615 meters per second squared, and that gives me a time of 18.16 seconds. And that sort of seems like a reasonable time for you to pull onto the interstate in, right? About 1/3 of a minute. All right, now remember we need to make sure that our number is the correct number of significant figures. You see, I forgot that, and I signed off on these, put a square around them with way too many significant figures. So how many significant figures do I have? Well, I have 2 here. I have 1, maybe 2 here, and 1, maybe 4 here. Unless I'm told otherwise, I'm going to assume that I've got 2 significant figures. Okay, and if you're not sure, write down your logic. So if you're doing a test and you're doing all this thinking, write down, tell me what you're thinking, and if you're thinking something that's reasonable, I can give you part credits or full credit for it. Okay, so let's assume that's two significant figures. So for my acceleration, that would be 4,900 miles per hour squared, or 0.62 meters per second squared. And for my time, that would be 5.1 times 10 to the minus 3 hours, or 18 seconds. Okay, so now these are my final answers, rounded off to the correct number of significant figures. And be careful to do that on a test. Make sure that you get yourself off to the correct number of significant figures. Okay, so let's do a fourth problem now. This problem is slightly different. And why is it different? Well, let's read it and find out. I've got a rock that's tossed straight upwards with a speed of 20 meters per second. When it returns, it falls into a hole that's 10 meters deep. What's the rock's velocity when it hits the bottom of the hole, and how long is the rock in the air? Okay, so I've got two things that are a little bit different here. First of all, I'm solving for a speed. We haven't done that in any of the sample problems yet. And secondly, I've got something that's moving up and down. So now reading this problem, I see I have a vertical problem here, a free fall problem. So I'm going to have to use this second set of equations this time. Okay, so let's draw a picture now. I've got a rock that's tossed straight up with a speed of 20 meters per second, and it returns and falls into a hole 10 meters deep. Now they don't tell us in the problem what height the rock is tossed from, so unless they tell us, we're going to assume that it's tossed from ground level. So we're going to start off, and now I'm going to put my positions as being y instead of x because I've got something that's going up and down instead of straight across. Okay, so it's going to start off from y initial of 0 meters. It goes up in the air, comes back down again, and it lands at a y final that's 10 meters below the ground. So I'm going to put that down as negative 10 meters. So my y initial is 0. My y final is negative 10 meters. Okay, what else are we given in the problem? We're told it's tossed up with a speed of 20 meters per second. So I've got my v initial is 20, and it's going upwards. So it's plus 20 meters per second. When it comes down, I don't know how fast it's going. I do know that it's going down. So remember, if it's going down, that should be a negative answer. So when we solve our problem, make sure that our answer gives us a negative velocity. How long does it take? Well, we don't know. That's what we've got to find in part B. And what's its acceleration? Well, the acceleration isn't given in the problem, but we know that for free fall, the acceleration is equal to negative g. Okay, so we're going to use this set of equations here. We're going to put in 9.8 everywhere there's a g. Okay, so let's solve the problem. So the two things I don't know this time are v and t. And I need to solve from these bottom sets of equations. So let's see. Equation 1, I don't know v. I know v initial. I know g, of course. I don't know t, so I can't use that. Let's see this one. I know y. I know y initial. I know my v initial. I don't know time. I know g, and I don't know time. So this is an equation I could use, but it's not going to give me velocity. This is going to give me the answer for part B, but not for part A. All right, how about equation 3? I don't know v. I know v initial. I know g. I know my two heights. So I could use equation 3 to solve for part A. So for part A, I'm going to use equation 3. V squared is equal to v0 squared minus 2g times y minus y0. And fortunately here, we don't have to do any algebra at all. We want to find v, and that's what we already have on the left side of the equation all by itself. Now, of course, we've got v squared, so when we solve for it, we're going to get the square of v, and we're going to have to take the square root to get our answer. So let's go ahead and do it. Everything's in the correct units. We've got everything in meters and in seconds. So just plug in initial speed, 20 meters per second squared, minus 2g G is 9.8 units meters per second squared. My Y, final position, is negative 10 meters. Initial position is 0 meters. Now, you need to be careful when you're doing up and down problems to make sure if the thing is below where it starts, you need to put the position in as negative. Okay, so what does this do? Well, 20 squared, that's 400. If I square the units, I get meters squared per second squared. Now I've got a negative and a negative. So this here is minus 10 minus 0. So it's negative 10. I got negative times a negative, which gives me a positive. So I've got plus 2 times 9.8 meters per second squared times 10 meters. Okay, so I get a final answer that V squared is 596 units or meters squared per second squared. Okay, to get my V, I need to take the square root of V squared, and I get square root of 596 meters squared per second squared, and that gives me an answer of 24.4 meters per second. The square root of meters squared is meters, square root of seconds squared is seconds. All right, now what have we left out? Now remember, the square of a negative number is positive and the square of a positive number is positive. So this V could either be plus or minus the square root of V squared. And remember, we said this thing's going down, so it must be negative. So we should put a negative sign in front. So now I've got my V final is negative 24.4 meters per second. Need to put this in significant figures. In significant figures, if I look at this, I can't tell whether it's 2 or 1 significant figure because I've got that 0 in there. I'm going to assume this time it's 1 significant figure because I don't have anything that's better than that. So it's minus 20 meters per second is the final speed. Okay, so we've got the answer to part A. Part B, how long is the rock in the air? Okay, so now I want to solve for the time. So I said I could use equation 2 because I know y initial, v initial, g, I just don't know t. Or now that I know v, I could use equation 1. So I could use now either equation 1 or equation 2. I would preferentially use equation 1 now if I'm sure that I got my answer for part A correct, because that would make it so that I had to do less algebra to get t. If I use equation 2, I'm going to have to use the quadratic formula to rearrange it to solve for time. So preferentially, I would use equation 1. But let's do it both ways. Okay, so equation 1, v is equal to v0 minus gt. I'm trying to solve for time. So I've got v minus v0 is equal to negative gt, or t is equal to v minus v0 over negative g. So put in my numbers, my final speed, and again remember at this stage in the problem, don't use your rounded off final answer. Put in as many significant figures as you can. So negative 24.4 initial speed is plus 20. And again, make sure you put these in the right order. And I've got negative 9.8 meters per second squared on the bottom. So on the top, I've got a negative. On the bottom, I've got a negative. And that's going to give me a positive time. And that's what we want, right? We have to have the time being positive. So if I put that into my calculator, I get a time of 4.53 seconds. And again, if I assume that this is only 1 significant figure, I'm going to have to round that off to 5 seconds. 4.53 rounds off to 5. Did my units work out correctly? Well, let's check. I've got meters per second on the top, meters per second squared on the bottom. So a meter is going to cancel out, a second is going to cancel out, and that'll leave me with just a second. All right, how about if I solve it the other way? So now if I use y is equal to y0 plus v0t minus 1/2 gt squared. and solve the quadratic equation. Let's go ahead and plug in what our numbers are. So y is equal to negative 10 meters. Y0 is 0. V0 is plus 20 meters per second times the time, which we don't know. That's going to be in units of seconds, minus 1/2 of 9.8 meters per second squared times the time squared. Okay, so if I just solve that, and I'm going to rearrange it so that it's in the form of 0 is equal to 10 meters plus 20t minus 4.9 t squared. Now I've dropped my units for now just to make it a little bit simpler. Okay, so if I look at this now, I need to compare it to the form of the equation. 0 is equal to at squared plus bt plus c, and you know that's the quadratic equation, and the solution for that is t is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, so that's something you should know from high school. All right, so put in my numbers. What's a? A is the thing that I have in front of the t squared, so it's a is negative 4.9. What's b? B is the thing that's in front of the t, so b is equal to plus 20. And c is equal to 10 meters. So if I put that into the equation, I get t is equal to negative 20 plus or minus the square root of 20 squared minus 4 times negative 4.9 times 10 over 2 times negative 4.9. And if I do my numbers, that's negative 20 plus or minus the square root of 24.4 over negative 9.8. Okay, so what are my two solutions? The two solutions are, if I use my plus sign, then I'm going to get plus 4.4 on top, divided by minus 9.8, and I get negative 0.45 seconds. And that's a negative time, so that's impossible. That happened before it started. What's the other solution? It's negative 20 minus 24.4, so it's negative 44.4 over negative 9.8. So two negatives is going to give me a positive, and I get plus 4.53 seconds. Exactly the same answer that I had solving it the other way. And again, I have to round that off to one significant figure, so I get a time of 4.53 or 5 seconds. Okay, the last question that we're going to do is a bit of a longer question, but you'll see that it's not really a harder question. So we start off, we say a light rail train going from one station to the next on a straight section of track, so that means it's a one-dimensional problem, accelerates from rest at 1.4 meters per second squared, so that's the acceleration, for 15 seconds. It then proceeds at a constant speed for 1100 meters before slowing down at 2.2 meters per second squared before it stops at the next station. What is the total distance between the stations, and how much time does it take the train to travel between the stations? Okay, so this seems fairly standard. All the things are there that we had in the previous questions. The thing that makes it more difficult is that we sort of have three different sections of which we're talking about. So let's start off and draw a picture of what we have. So initially we have the train. Let me get a different pen. Initially we have the train at rest at time t0 equal to 0, let's say, and a position of x0 equals 0. Then it goes along with from initial speed of 0, it accelerates at 1.4 meters per second squared for 15 seconds. Okay, so at some time later, t1 15 seconds, it stops accelerating. After that, it proceeds at a constant speed. So whatever speed it was going when it hit 15 seconds, it keeps going at that speed for a distance of 1100 meters. And then it starts to slow down, and it slows down until it's stopped at the next station. So we've got 4 different times that we're talking about. T0 when it starts off, time is 0, position is 0, speed is 0. T1 when it starts going along at a constant speed. T2 when it starts slowing down. And T3 when it's stopped at the final station. So let's call these regions A, B, and C. Okay, so now we're going to have to figure out what we know and what we don't know at each of these lines that I've drawn on here. Okay, so I've got position, initial and final, position at each line, time at each line, and speed at each line. Okay, so x1, I don't know. Speed at 1, I don't know. I know the acceleration during period A. All right, during period B, it goes along at a constant speed. So constant speed, that means that the acceleration is 0. Its position, when it gets to the end of period B, I don't know. Its speed, I don't know what it is, but it's the same as what it started with because it's moving at a constant speed. So if I can find V1, I know what V2 is. All right, then what happens during period C? During period C, it continues on and it slows down at 2 meters per second. So in this case, I've got an acceleration at 2.2 meters per second squared. And it's slowing down, so I put a negative sign on that. It's decelerating. Its final position at T3, I don't know that. Its final speed, I know is 0 because I said it stopped at the last station. Okay, so what is it that we want to solve in this problem? We want to know what's the total distance between the stations. So that's going to be x3. So they're asking us to find x3. And how much time does it take? So it wants us to find T3. All right, so how are we going to do it? Well, to get position 3, I'm going to have to find the position at each of these stages and add them all together. Okay, and the time, I'm going to have to find out how much time it takes to go the whole length. So basically all we have to do is we have to do what we did in the previous problems. We just have to do it 3 times. We have to solve it once at T1, once at T2, and once at T3. Okay, so let's start off with region A. So region A, I know I've got an acceleration of 1.4 meters per second squared. I know my time is the time between initial and final, so that's 15 seconds. I don't know my position at the end. I don't know my speed at the end, but I know my position at the beginning is 0 and my position, so my velocity at the beginning is 0. Okay, and what do I want to find? I need to find the position and I probably need to find the speed. So let's go ahead and find both of those. Okay, so let's look at equations. What do I have? Now I'm moving horizontally, so I'm going to use this top set of equations. First equation, what do I know? I don't know my final speed. I know my initial speed. I know my acceleration. I know my time. So that's an easy way to find V1. So let's do that. V1 is equal to V0 plus A times T. So V0 is 0. My acceleration is 1.4 meters per second squared. And my time is 15 seconds. Okay, so my final speed is going to be 1.4 times 15, which is exactly 21 meters per second. Okay, is that a reasonable number? Yeah, it probably is a reasonable number for the train to be traveling at. Okay, so now the next thing, I know my V1 now is 21 meters per second. And since I know V1, I also know V2 is 21 meters per second. So you see, we're rapidly filling in the things that we don't know. Okay, next thing is let's find the position. How far along the track is it when it gets to position 1? Okay, well, now I need an equation that's got x in it. So I've got this one here. Let's see if I know enough to do that. I don't know x. I know x initial. I know v initial. I know my time. I know my acceleration. So I could use equation 2 to give me my position. So x is equal to x initial plus v initial t plus 1/2 at squared. Let me go ahead and put x1 on that so we know that's what we're trying to solve for, the position at point 1. Okay, so position at point 1 is going to be x initial, 0, plus v initial, which is 0, times the time, which is 15 seconds, plus 1/2 times the acceleration, 1.4 meters per second squared, times the time squared, so 15 seconds squared, and that gives me 157.5 meters for my position. So now I know I've got 157.5 meters. Okay, so I've got everything I need for position 1, and remember, this isn't my final answer, so we're not going to round anything off to significant figures at this stage. Alright, so now position 1, let's go along to position 2 and see what do we know. Okay, well, let's see. Position 2, now we know our speed, we don't know our time, we don't know our position, but hey, wait a minute, we know that it started off at 157.5 meters and then it traveled 1100 meters, so it's actually 157.5 plus 1100, so we know that position. Okay, so if we look at stage B, x2 is just x1, 157.5 meters plus 1100 meters, so that's 1257.5 meters. Okay, so we've got that. So what do we not know? The only thing we don't know is the time. Alright, so we want to find the time. We've got initial and final speed, we've got initial and final position, and we've got initial time, and we've got the acceleration. Okay, so let's go back and look at these equations now. Now, first equation, remember I'm trying to find the time, so the first equation has time in it, but it doesn't give us anything because we know that v initial and v final are the same and the acceleration is 0, so it's just going to get rid of the t in there. So we can't use that equation, so the only other equation that involves time is equation 2. So we're going to have to use equation 2. Alright, so I've got x is equal to x0. Now remember, I have to put in my initial and final positions here, and my initial position is x1, my final position is x2. Okay, my initial velocity in this case is v1, and the time in this equation is the time between t2 and t1. So my time is going to be t2 minus t1. Okay, and let's just write that as t, just to make our equation simpler. And we're going to have 1/2 a times t squared, where again t squared is going to be t2 minus t1. So we'll solve for t, and then we'll get t2 by just adding 15 seconds to it. Okay, so plug in our numbers. Well, actually, first let's plug in our numbers a little bit to make the equation easier to solve. Technically, what we should do is just algebraically solve for the time, which is going to make us use the quadratic formula like we did in the previous problem. But we know that a is equal to 0. So since a is equal to 0, what we really get is x2 is equal to x1 plus v1, which is 21, times t. And again, I'm going to replace t2 minus t1 as t. And 1/2 at squared is going to be 1/2 0 times t squared. So that just disappears. So my equation now is x2 is equal to x1 plus 21t. So that means that t is equal to x2 minus x1 over 21. So that's going to be 1257.5 minus 157.5 meters over 21, and that gives us a time of 52.38 seconds. Okay, so the time that it takes to go from T1 to T2 is 52.38 seconds. So T2 is equal to 52.38 seconds plus T1. So it's 52.38 plus 15, or 67.38 seconds. Okay, so now I've got, going back to my picture, 67.38 seconds is T2. All right, now what's next? Well, remember, we're trying to solve for x3 and t3. So let's just go on to stage C, and we're going to do exactly the same things that we did. All right, so I know my initial speed and my final speed. I know my initial position. I don't know my final position. I know my acceleration. I don't know my time. All right, so I want an equation where, knowing my initial and final speeds and acceleration, I can get my final position. I don't know the time, so I can't use either equation 1 or equation 2, so I'm going to have to use equation 3. So let's look at this, v squared, and now remember, v final in this case is going to be v3. V initial is going to be v2, what it started off with in that period, during period C, plus 2 times the acceleration times x3 minus x2. That difference in position, that displacement, is the displacement during period 3. All right, so I want to solve for x3. So let's rearrange this a bit. So I get v3 squared minus v2 squared over 2a is equal to x3 minus x2. In other words, x3 is equal to x2, which we know, plus v3 squared minus v2 squared over 2a. All right, so just plug it in and we should get our answer. x3 is equal to x2. x2 we said was 1257.5 meters. Plus, now I've got v3 squared. v3 is 0. We end up going at a speed of 0. It's at rest. v2 squared. v2 is 21. So you see I've got a negative thing on top over 2a. Now my acceleration in this case is negative because I'm slowing down. So we've got negative over negative, which is a positive. And if we put that in, we get x3 is equal to 1357.73 meters. And that's our final answer for A. So now I need to be careful about significant figures. Look at what we're given. That's 2 significant figures. That's 2, that's 2, that's 2. So we need to answer in the least number of sig figs. So I got to round this off to 2. So that's 1400 meters is the distance between the stations, between where it starts and where it ends up. Okay, last thing, I need to find out what's my time. All right, so I want to find time, and now I've got everything. So I've got my x3 is, again, remember when I do my calculations, I got to put in the unrounded numbers. Okay, so I know everything now except time. So I want to find the simplest equation I can use to find time, and so that's going to be equation 1. All right, so I've got v3, that's the final speed in position C, is equal to v2, that's the initial speed for position C, plus a times t. And t in this case is going to be t3 minus t2. It's the time between these two positions. All right, so solve for t. T is equal to v3 minus v2 over a. v3 is 0 minus 21 meters per second over a, which is negative 2.2. So again, negative over negative is a positive. We always have to have a positive time. So I get 9.55 seconds. Okay, so this distance in here is 9.55 seconds. So I need to add that on. T3 is going to be T2 plus 9.55. So it's going to be 67.38 seconds plus 9.55 seconds. which is equal to 76.93. And again, I got to round that to 2, so that rounds off to 77 seconds. Okay, so our final answers are 77 seconds and 1,400 meters. Okay, so what started off looking like a really complicated problem, in the end, just boiled down to solving 3 individual problems like we did in the earlier things, and then correlating it together. And this is why it's really, really important to draw a picture. When you start off, draw a picture and find the numbers that are in the problem, and put them where they belong in the picture. And that gives you an idea of what you know and what you don't know. And as soon as you know those things, then you can go ahead and choose which equations you're going to use to solve the problem. The most important thing is don't panic. Remember, on a test, we're going to give you problems like you've seen before. So even though it's a train, instead of in class we did a person running or we did a car, it's basically the same problem. And you always do it the same way. Read the problem, draw a picture, write down what the things are that you're given in the problem, and then figure out which equations you need to use. The hardest thing that you'll encounter is actually doing the algebra to rearrange the problem to solve it correctly. Okay, so make sure you do as many problems as you can. Do problems from the back of the chapter. Do all your homework problems. Go online, look for problems, find out the physics textbooks, because by doing more and more problems, you get more confident with doing the problems, and you're much more likely to be able to do the problems on the test.